Howdy, everyone. Happy fall. Um, Tell me if you're having trouble hearing me. Hopefully we're okay. Um, Today, denial of service and firewalls and intrusion detection systems, a bunch of techniques that can be used for network security. We're kind of winding down here. We're getting to the near the end of the class. After today, the rest of the class will be mostly fun topics, hopefully. Hopefully fun. Aspirationally fun. All right, so we talked last time about DNS security, the security challenges in DNS, how DNS works, and DNSSEC, which is a method to add end-to-end security to DNS with the clever idea that each data item provides its own security with the digital signature, and it's designed so that uh, it provides security even if some of the intermediate caches or servers that are temporarily storing data for you are malicious. Um, Today, I want to start by telling you about denial of service attacks. And there's a whole bunch of them. And denial of service is about we talked about the three main security properties: confidentiality, integrity, and availability. Denial of service is an attack on availability. Okay, so denial of service attack is where I do something and now you can't use your computer, or you can't use that website you wanted to use, or your mobile app stops working. Okay, so that's a denial of service attack. Um, let's suppose that you wanted to, I don't know, prevent me from calling a Lyft on my way home this evening. What are some attacks that maybe you could imagine doing to try to achieve that goal? Yeah? Sweet. Get a bunch of computers. Keep calling my phone so that I'm like on the app. I start like entering it in, and then a phone rings. And I'm interrupted. And then I like block it, and I keep going, and another phone rings again and again and tries to like disrupt me. Another attack. So like book a bunch of Lyft rides so that all the Lyft drivers in the area are fully occupied. Uh-huh. Uh-huh. Okay. Okay, good. So you're gonna like use up my attention. You're gonna use up the all the available Lyft riders. Any other attacks? Oh yeah, it is kind of cold. Thank you. Does anyone else have any thoughts? We could try physical security. Anything you could do that might work from a physical security perspective? Maybe a thought there, I see. Like anything, it's not digital stuff, but it's like, I don't know, if you whack me over the head with a hammer, that would be that would count. Oh, cut all power lines to my building I'm in or to Berkeley so that I can't, maybe the internet. I can't get any internet. Cool. Okay. Uh-huh. Hit me on the head too many times. Yeah, I think once will be enough. What else? Yeah? Book a bunch of rides so all the drivers are tied up. Yeah, and I go on there and I'm like, why does it say 47 minutes until my next available ride? Yeah? lot of ed questions. So I'm like, oh, I can't go home. I have to answer all these ed questions. Yes, then mark them urgent. Anything you could do to the go after the Lyft server? I mean, I'm willing for you to go kind of, you don't have to be super realistic. We're just brainstorming. We're just trying out ideas.
Like send a lot of requests to the list server.
Send a lot of requests to the web server. What do you think that might do if you send a lot of requests to the web server? Maybe it'll like get overloaded and yeah, be unable to answer my very important request. Anything else? Any way you could make that work really well? Any way you could like, I don't know, maybe the server can handle a lot of requests. Can you think of any ways to like really boost up the strength of that attack?
Wait, what can the server do?
Yeah, what kind of server? I don't know. Make up something.
No, like you said something before your like the server can like mitigate this.
If you were going to send a lot of requests to the Lyft server to try to overload it, what kind of request would you try to send? What would you look for? There's many different kinds of requests you could send. Anything might work. Is there any, if you had a choice of a lot of different kinds of requests, is there any kind of request or like feature or characteristic of a request that would make it really good, make it really effective for attacking? What are you thinking?
Something that doesn't have any kind of therapy involved, so it has to respond with something relatively hard. So maybe like a DHCP request or something over the if you are on the same global area network, I guess I'm just like reset, eject the server, but
Awesome. Lots of great ideas. Okay, first of all, maybe I look for a request that I don't have to identify myself, or there's no verification. So it's not easy for them to figure out who's doing the attack or to block the attacker. And then another thing you said was something where the attacker can send a request and the server has to respond with something really long. Like maybe send a request, I want to download your latest app, or I want to download something, some large file. Then the server has to do a lot of work to respond to each one of those. The attacker does a little bit of work. The server has to do a lot of work. Yeah, so that would be really attractive if you can find some kind of request like that. That's a asymmetry, looking for some asymmetry. And then the third thing you said was if the attacker was on the same network as the server, maybe you could do some kind of like ARP or DHCP spoofing or something to like block its network connections. Yep. Any other ideas? Okay. I like the ideas you came up with, and you came up with a lot of the themes that I wanted to hit on. So let me kind of walk you through some of the themes that I wanted to hit on, and we'll kind of map them to what you came up with. Um, Denial of service. We already said what denial of service is, but there's many reasons why someone might want to do a denial of service attack. One reason is an unethical competitor might want to like make their other businesses they're competing with look unreliable. Another one is criminals. That's kind of maybe not so common, but a common one is criminals using this to try to extract a ransom payment. And so there was a while where there was quite a lot of denial of service attacks where criminals would go after online casinos were a really juicy target, and they would block their website so people couldn't go to their website and bet online. And then they would send a ransom note that said, "Look at all the money you're losing. You know, it'd be a shame if nobody could reach your website all week long. If you would like protection services to make sure that your website is reachable, we have a, very affordable payment plan." So ransom. And we can continue to see some kind of denial of service attacks like that today with ransomware, where hackers will hack into the computers of like small hospitals or small businesses where there's some security flaw, and then the hackers can like download all their data and delete all their data and say, if you want your data back, pay me $50,000. Otherwise, you won't be able to use your computer systems, and all your doctors are going to have to work using paper records. Okay, so that's probably the dominant motivation for denial of service attacks today, is to blackmail, ransom, extract some payment. Could also happen for like political purposes. One political group takes down the website of one of their ideological opponents. And also, there was a time when we saw this in online games. It's a way to get ahead. And if you're playing a two-player, like, a head-to-head shoot 'em up game against some opponent, and you could figure out the IP address of your opponent, then there were services, I think they were called booter services, where you could pay $10 and the service would overload your opponent's computer so that your opponent couldn't play the game for the next couple of seconds, and you had a big advantage and you could win the game. It's amazing what ways people will cheat to get an advantage in a game. Okay. And this is kind of like there's a criminal underground who will do denial of service attacks for hire. They've worked out the most cost-effective ways, and you can hire them. You don't have to be an expert. And this is, 15 years old, but you can kind of see the payment at the time, what the cost was. The surprise is not just that you could buy this, but how affordable it was. Like, you and I could afford a denial of service attack against some random person's website. It's like hire a hacker kind of thing. Yeah. Today we have some better defenses, which I'll talk about in a little bit. And this was then used for extortion quite a bit. Also, we saw some bad guys use this to supplement other attacks they were doing. It's kind of funky, but like they would send a fake email to the victim saying, our banking website is experiencing problems. Please log in at this alternate URL. And then they would do a denial of service attack against the real banking website, so that if the person went to the real banking website, they're like, oh yeah, they are experiencing problems. Wow, I should go to that alternate URL. I don't think it's a very super effective attack, but sometimes denial of service can be used in concert with other attacks to make it harder to detect or make the attack more convincing. So the strategies for denial of service, at a very broad level, we could categorize these. One set of strategies is to exploit some flaw in the program, and the other set of strategies is to exhaust some limited resource and overload the computer. So exploiting program flaws, for instance, any of the vulnerabilities we saw before could be used for denial of service. If you can find a buffer overrun vulnerability in a server that lets you execute malicious code, you could execute malicious code that causes the program to crash, to terminate. So that's kind of not very interesting or new. We've already seen program flaws, so I don't really need to say much more about that. You already know a lot about that. But the other category I think is maybe interesting and different, which is even if the server or the app or the website or the program has no bugs, no program flaws, you often can still do denial of service attacks by exhausting some limited resource. And everything, computers and network, everything has some limits on how much bandwidth it can handle, how many packets per second, how much computation it can do per second. And so an attack strategy is an attacker picks some resource that's limited and consumes all of it. So there's none left for like useful work or for legitimate users. And there's many different ways to do that. But typically what the attacker is doing is looking for a bottleneck. So some part of the system that is the most constrained, that has the least resources. Like if you have a network connection that goes over multiple hops, some of those network links might be very high capacity and some might be very low capacity. And the overall capacity will be limited by the capacity of the smallest link. And so the attacker tries to overload that smallest link, the bottleneck. For instance, the bottleneck in my internet connection when I'm working from home is my like DSL internet connection from my home to the internet service provider. So that's the one that the attacker targets and tries to overload. And some of these attacks work at the application level. They try to exploit overload some resource in the application, and some of them work at the network level. They try to overload some network link or some network router or something along the path. And maybe those are a little interesting to see and notice that distinction because you cannot solve a network level denial of service by modifying the application because the network link gets overwhelmed before legitimate packets can't even make its way to the end application because the network gets overloaded. But potentially you could defend against application level denial of service by modifying the application in some way. So defending against network level denial of service, the only feasible defense is to modify the network somehow. Okay, so application level denial of service targets some limited resource that the application uses. The application might be a program running on a server, it might be the app running on your phone, it might be the browser on my computer. And typically here, these attacks rely on asymmetry, where the attacker can put in a little bit of effort and force the victim machine to consume a lot of resources, typically. So here are some examples to get a little more concrete. If there's a network server that I can run code on, run a program on, then there's lots of ways that I could cause a denial of service against that server. Like if you're doing a project on one of the Hive machines and I can also log into that Hive machine, even though I don't have administrator or root access, I can probably cause that machine to get overloaded and prevent you from being able to make progress on your project on that Hive machine. Some examples of ways I could do that. I could write a little program that opens a bunch of files on the file system, writes a ton of stuff to them until the disk is full. And then when the disk is full, it's a shared disk that's shared between me and all the other users on that machine. All the other users on that machine, there's no disk space. So everything they try to do starts failing with error messages because the programs are trying to try to create some temporary file or something. There isn't any disk space to create it, and the program's like, I can't continue, I'm stuck. How would you defend against this kind of denial of service attack, where the attacker consumes all the available disk space? Yeah? Partition the disk. Do you want to say more about what you mean by that, or do you want me to take a guess? Cool. Maybe we have a disk that has 500 gigabytes, and there's 500 users, so we each give each user 1 gigabyte of disk space. Good or bad solution? Pluses or minuses? What do you think? Seems a plus. What's a plus?
The US has to be conducted by someone.
Yeah.
So if that person does not, but can they change it so that their portion on the disk overlaps with someone else's portion on the disk?
Oh, we should think about whether there's overlap. Okay, simplest scheme, each user gets assigned their own 1 gigabyte, no overlap. Then it should be good and secure. Yeah. If I fill up my 1 gigabyte, it doesn't harm you. You still got a gigabyte for you. Yeah? Ah! Okay, yeah. So if an attacker can create a lot of accounts or identities or users, Maybe that's bad.
In here, that's also the problem with us, which is that, see, I'm gonna create an account, but you could detect that I can create 1,000 accounts. But actually, my neighbor's fridge, which also has a computer technically connected to the internet, and they can secure it, that smart fridge is actually also gonna create an account. And it's a very different idea from mine. And it seems completely legit. And so now I'm gonna have 1,000 smart fridges creating accounts and writing them divided data.
Totally. Yeah. So if this is an open system where anyone can create an account on it, then we got a major problem. There's no limit on the number of accounts the attacker can create. They can use up basically all available space and limit everyone else. There's another problem. It's not a security problem, but there's another reason why we don't do that on the Hive machines. Does anyone? Yeah? Because everyone's really super limited. Most of the time, most of us are not using our available disk space. It'd be really nice if, like, if I need 10 gigabytes today and you need 10 gigabytes tomorrow, as long as the space is available, we can use it. Yeah. Yeah. So it's kind of limited to partition things up in that way. But yeah, so this is a general strategy is you have some quota or some limit on what each user can use. And that works better if you have a fixed set of users. And it works poorly if anyone can create an account, if there's no limit on the number of users or accounts someone can create. Yes. Yeah. Yeah, that's going to be another defense. Okay. Yes. Yes. Um, Let me come back to that one. But basically, I don't know of any really good defense. When you have a open system that anyone in the world can connect to, um, I don't think there's going to be any full security. What you can try to do is to increase the cost for an attacker. Generally, so this asymmetry, the problem comes when there's a large asymmetry. The attacker can do $1 of work and force the server to do $1,000 of work. That's bad because low cost for the attacker causes a high cost for the good. So there's no like strong defense. Instead, what we do is we just try to look for cases where this asymmetry may be present and reduce the asymmetry so that the attacker's cost will go up. Yeah. Okay, so good. You got two general techniques here, quotas or limits, and make sure you identify the user. Here's another example attack. If the attacker can run programs on the same server as you, the attacker could write a program that allocates all available memory and starts using the memory. Now there's no memory, there's no memory for your program, or your program is fighting to get access to memory and keeps getting paged to disk, and you get really bad performance and everything's really slow and you're like, why does this machine suck? How could we defend against this? Same kind of situation, some limits on the amount of memory that each user can use or something. Maybe we don't have hard limits, but we say, if there's more demand for memory than there is available memory, then we're going to put some limits on you. If there's plenty of memory, then you can have as much as you want. You can imagine various policies there. You could say something like, you can have a lot of memory for a short amount of time, but then, kind of averaged over a time period, your memory usage has to be limited. Yep.
And delete them, clear up files?
Usually the permissions are set up so that I can't delete your files. That would really suck if I could go delete your files. Yeah, so the victim usually cannot go delete the attacker's files. Yeah. You would need a system administrator who has the power to go delete people's files. And the system administrator would probably go figure out who the annoying user is and like cancel their account and then delete their files or reboot or something. Okay, and there's lots of examples like this because there's many different kinds of limited resources that could be overloaded. Another one is the amount of processes running. The attacker could start lots and lots of processes, and each one uses some resources. The attacker could start reading and writing to disk, and the I/O bandwidth to disk could get totally filled up with the attacker's reads and writes, leaving very little bandwidth for legitimate users. There's lots of limits in a system that an attacker could try to target and overload. We could also look at another kind of attack on applications that we can look at is algorithmic complexity attacks. This is kind of interesting. This is like CS61B type stuff. If we have an application that sorts some data, maybe that's uploaded by a user, using quicksort, let's say, there are some inputs that will cause quicksort to take quadratic time. So the attacker could upload data that makes quicksort really slow. And then the application will spend a lot of CPU time running quicksort for this quadratic time sorting algorithm. And if the attacker uploads a 100 megabyte file with a million records, then quadratic time, a million squared, might be a lot of computation needed by the quicksort. So even though the server was not coded with a loop in there to like use lots of CPU, if it has an algorithm that can be induced to use lots of CPU, the attacker might be able to provide an input that causes the server to start using lots of CPU to serve the attacker's request, leaving not much available for the legitimate users. Yeah. Yeah, so then a reasonable defense would be to have some scheduler that limits how much CPU can be used for each user. Maybe like sets equal priorities for all the users. If there's more demand than there is available compute, then it kind of like switches equally between the users so they all got a fair share of the CPU. Absolutely. Yeah. Except then you need a scheduler. You need a way to know what user has placed each request, and the scheduler has to be aware of that. So if this is like a web service, the operating system has a scheduler that's switching between processes. But all of these requests are being handled by the web server. So from the operating system's perspective, they're all running under the same user ID. So the operating system scheduler doesn't have the visibility to know what the original user account was. So scheduling would need to be done like in the web application would need its own scheduler. So it can be a little tricky to do that scheduling. Conceptually, absolutely. A very good defense. Yep. Only concerned with time and space. I guess so. Time and space are kind of at some fundamental level the resources that are limited, but it might be other resources too. It might be the amount of I/O bandwidth. It might be the net how much bandwidth is available in the network link, how much bandwidth is available to read and write to disk. Could be either. Uh-huh.
Imagine that if it goes from like this space complexity from like level 1 to level, and in order to have like maybe the runtime go from 12 square level, then you sacrifice a bit of space for that. So the one with the expected like faster runtime might actually take up more space. So like that's not strictly that.
Yeah, I don't have any simple answer about how to trade off between space and time, or that how to suggest that one is more important than the other. Sorry. You're right. Often you can find algorithms that use some more space to use less time or use less space but take more time? I don't have a simple answer. I guess it's some engineering trade-off. You look at the system and you look at how much of those resources you actually have and try to make a reasonable judgment. So for instance, you might replace quicksort with merge sort because merge sort, even though their average case runtime is the same, the worst case running time of merge sort is much better than that of quicksort. The difference only appears for some very rare inputs. But if you're worried about an attacker who can provide those rare, very rare inputs deliberately, then the worst case running time might matter. Okay? So that's the idea of algorithmic complexity attacks. Let's test you on this. If I'm worried about algorithmic complexity attacks, denial of service attacks of this form, is a hash table a good choice or a bad choice? Hash table is a good choice. Ooh, let's split up into pairs. Let's split up into pairs, talk to someone next to you, figure out whether you think it's a good choice or a bad choice, or if you can't decide, come up with some arguments for why it might be good or why it might be bad. Okay, talk to someone next to you.
If we're using just like that's just there's what we were on it does it has people and it's all the all like they're people one we're all and finding from there and it's a people and in the list well yeah we'll in the first case where every number of titles so yeah, it does not, but like, is there something we're supposed to compare this with? Yeah, so I don't, I think. It does have.
Yeah, I don't have like a. Yeah. Yeah. That's. Yeah.
Okay, temperature check. How many think a hash table would be a good choice? How many think a hash table would be a bad choice? How many would like some help talking it out? Okay, okay, all right. Someone want to give me a reason or an argument why a hash table might be a good choice? Yeah?
You don't have all the stuff in one bucket, and you usually have it spread out. But so it's usually advertised O1. But if you do have all of them in the same bucket, then it's going to be O of N.
Uh-huh. Yeah, usually O of 1. Yeah?
If you're already assuming, yeah, this can go up to O of N and you're treating it as that, then like, it could be fine.
Okay, worst case is O of N time, and if you're already like prepared to handle O of N time, insert lookup, it's no surprises there. Anyone want to give me an argument for why it might be a bad choice? Sure, an argument. My algorithm that was O of 1 in all my testing could turn into O of N if I'm handed a worst case inputs. Any other arguments?
I feel pain, so I can lay out better, bad or good.
So I would, yeah, go ahead. Great. Two suggestions that maybe we need to compare it to something. I like that. I like that. So what would be some alternatives we could compare it to? Does anyone want to suggest some alternative to a hash table that we could consider instead of, if we weren't going to use a hash table, what could we use instead? A red-black tree? Okay, from algorithmic complexity attack perspective, how would you compare a hash table to a red-black tree? What's the average case time for insert or lookup in a red-black tree? O of log n. O of log n. What's the worst case time in a red-black tree for insert or lookup? O of log n. Red-black trees are a crazy data structure that when you insert, you make sure to adjust things so that it stays balanced. It's an example of a self-balancing binary tree. So it's designed to make sure that its depth will always be O of log n, and you'll never have this really imbalanced thing. And so as a result, the red-black tree is this really complicated data structure where the worst case time to do an insert or a lookup is O of log n. Okay, so given that fact, if I'm worried about algorithmic complexity attacks, how would I choose between a hash table or a red-black tree? Pick the one with the better worst case. So the red-black tree would be better. Yeah. Yeah, I agree with that. So if I'm normal programming, hash table is a great choice. O of 1 time for insert and lookup on average. Awesome. Can't get any faster than that. Really simple and easy to implement. Awesome. I like it. But if I'm concerned about algorithmic complexity attacks, hash table's worst case is much worse than the worst case of a self-balancing binary tree data structure. So if I'm concerned about algorithmic complexity attacks, maybe I should rip out all my hash tables and replace them with tree map data structures using some self-balancing binary tree. For what? Good question. Storing some data that the user of your application can upload. What would be a good example? How about tags on your oh, sorry, I'm blanking on the photo website. You can tag your photos with some tags, and you can look up, search for a tag, and find all photos with that tag. Users can specify their own tags. You'd like it to be fast to put a tag on your photo or to like search for a tag. If it takes O of n time to search for a tag or add a tag to your photo, where n is like, I don't know, the number of photos I've uploaded or the number of photos in the database, that could be really slow. What would an attack on a hash table look like? With most hash tables, the hash function is not secret. There's no cryptographic keys in there. It's not designed to be a cryptographic one-way function. The hash function for hash tables, it's not too hard to come up with many inputs that will all have the same hash code. So I tag my photos with many different tags that all have the same hash code, or I upload many photos that all have that same different tags but the same hash code. Then in the hash table, they'll all map to the same bucket. And insert or search in that bucket will involve scanning all the items in that bucket. So the hash table will devolve to like a linked list. Even with current hashes, because the hashes in your favorite programming language are designed to be fast. They're not designed to be cryptographically secure. So another option would be to use a hash table, but replace the hash function with some cryptographic hash function. That turns out would also work. Okay, but basically what this means is normally in most programming we care about expected runtime, but if you're worried about algorithmic complexity attacks, then think about worst case runtime. How do we defend against all of these? We've started talking about some of the defenses. For many of the defenses, they start with first identify the user, which means we need some way to identify which user has sent this request. And then once we know, we can associate the user to each request or each action. Then we can do some kind of partitioning, like you suggested, to isolate the users so that one user's action doesn't affect other users, like we divide up the resources among the users. We can use quotas to put a limit on upper limit on how many resources each user gets. Maybe I have a 500 gigabyte disk and I say each one of you can have up to 50 gigabytes. And I'm just counting on the fact that most of the time, most of you won't use a lot of that. Another defense is to increase the cost for attackers of overwhelming the server. If the user sends a request that would force the server to do a lot of work to answer it, some expensive search operation, search for all entries that match this condition and that condition or that condition, that search is going to take the server a lot of work to do, then force the user to prove that they have some stake in this, that they have put in some work to try to reduce the asymmetry, to try to increase the cost for attackers. So for instance, on some websites, if you enter in a complex search on the website search, before they'll give you an answer, they show you a CAPTCHA and they force you to solve the CAPTCHA. And then when you solve the CAPTCHA, then they'll give you the answer. Why is that? They figure that way that bots can't send them thousands of complicated searches per second because the bots won't be able to fill out the CAPTCHA. Or, as you suggested, they could hire a service that will solve CAPTCHAs for them, but it's going to cost them a couple of cents per CAPTCHA. So it's going to cost the attacker money to send a lot of these complicated requests per second. And so it's going to increase the cost for an attacker of overloading their server enough that we can like mitigate or make the attackers go away or kind of get them to stop bothering us. Yeah.
How do have this already been work? Because like from what I know, those like there's no longer just like a questionnaire. Like, it's like pretty much all movement and all activity. So unless you have the human actually doing all the movements for the computer, in which case it's not really economic. So how effective does it work?
Yeah. So right now, when the bad guys have the CAPTCHA solving services, there's two strategies they use. You could probably guess what they are. One is humans. They hire humans, actual workers, sitting somewhere in the world where labor is cheap to sit there and solve CAPTCHAs all day long. Can you believe it? And the other way is AI. They try to code up some clever machine learning LLM agent, vision language model thing to solve the CAPTCHA. And it turns out that in practice, my understanding is that most of the black market CAPTCHA solving services use humans. They pay some poor schmo $10 an hour to sit there all day long clicking on solving CAPTCHAs. And the cost of solving each individual CAPTCHA is like a cent or a couple of cents because you can do it, 1,000 an hour or something like that. And the reason for that is because while some of these CAPTCHAs can be solved by sophisticated AI, if you know how to do like sophisticated machine learning, that is a rare skill. And if you have the skills to do sophisticated machine learning, you're probably going to just get hired as an ML engineer and earn, $100,000, $200,000 a year instead of going to work for one of these black market things. So it's actually cheaper for them to just use human labor than to code up the AI.
Like, I'm looking at the site now.
Yeah.
But reCAPTCHA V3 doesn't do any sort of like click on the images, right? nowadays, it's more, well, ML tracking your mouse and cursor sort of stuff and user tracking. So how does that work with humans involved? Because like, surely you would have the humans inputting all the data and trying to pass them down.
Oh, I see. I see. Yeah, some of the captures don't have you do any, don't have the user do anything. They don't have to click on anything. It's just like trying to observe mouse movements and like try to query information about your browser. And yeah, I don't know how those are bypassed. It's a good question. Maybe we could do some research and learn what the bad guys are doing. Yeah.
Is this one? Is that you like try to go over certain level of requests to the API using the API, then you charge.
It is related to pricing, yeah, because if the server is providing a service through some API and they're charging for it, then they can make sure that they charge enough that they're making a profit on any request. And then they don't care if someone sends a lot of requests if they're making a profit on every single one. It tends to be a bigger challenge for free services. The other defense, which is very common, is over-provisioning. If it's cheap to have a lot of capacity on the server, then you set up a server that has way more capacity than it needs in normal operation. And if attacker wants to try to overload it, the attacker is going to have to send a lot of requests. And if you can over-provision enough, then maybe you can make it difficult or expensive enough for the attacker that they're not going to bother. It sounds kind of far-fetched, but this is the #1 defense against network-based denial of service that's used today for the web. The #1 defense today is you use Cloudflare. And Cloudflare is basically a caching service that you set up your DNS so that if a visitor tries to go to your website, they're directed not actually to your server, but to a Cloudflare server that has a cached copy of what's on your website. And then Cloudflare goes to your website and fetches that page if it doesn't already have it cached. And Cloudflare has thousands of servers, tens of thousands of servers all around the world with an enormous amount of aggregate capacity to handle requests. So if 1 million people start hammering on your blog tomorrow, you don't end up with 1 million requests to your blog server. There's 1 million requests to Cloudflare. Cloudflare downloads one copy of that blog post and then sends it to all the 1 million people who are trying to access it. Cloudflare, because this is shared across all their customers, their thousands of customers, and most of their customers are not undergoing denial of service attack at any one point in time, can afford to have an enormous amount of capacity, massive amounts of excess capacity, like way more capacity than any one person doing one denial of service attack could use up. So it's a kind of like a statistical multiplexing amortization thing that maybe I need to have a network link that can handle a terabyte of network traffic to be able to handle denial of service attacks, because attackers can send up to a terabyte of data to my web service. I can't afford to do that for my website, but I can pay Cloudflare $5 a month, and they buy 2 terabytes of network connection, and it's just sitting there if it's ever needed. Most of the time it's not needed, but if my blog gets attacked, they put all that capacity towards my blog. And then when my blog is not being attacked, but your blog is being attacked, they put it towards your blog. So they have this excess capacity that can be used for whatever site's being attacked today, and they can shift around where it's needed. So it's kind of an interesting defense against denial of service. It kind of removes the incentive for denial of service because attackers can send a lot of requests and Cloudflare will be able to handle it. They just absorb it. Kind of funny. And everybody else can still reach that blog. And so the attackers don't really have much incentive to do it anymore because their denial of service attacks don't work. so long as Cloudflare has enough computing that they have a more than the attacker can generate. If they don't, then we got a problem again. And you can see how this could tend to like really encourage like a monopoly or a really big favor, a really big company that can afford to have a ton of capacity in case it's needed, shared among lots and lots and lots of customers. Yeah. Then that would be a problem. That'd be like a cool Aikido move. Yeah. If the attacker can get Cloudflare to attack themselves, then we've got a problem. Fortunately, Cloudflare is incentivized to like try to detect that and fix it if it happens. But absolutely, yeah. That would be really bad news if there was a way to do that. Is this a good time to take a break? Let's take a break. Let's take like a 2-minute stretch break. Stand up, get the blood flowing. It's good for you. Okay, let's keep going. That's application level denial of service. The other kind of denial of service is network level denial of service. Overload the network. Kind of very simple idea. One simple form of this is the attacker sends lots of data to the victim, tries to overload the maximum amount of bandwidth. Okay, so if the server only has a 10 megabyte per second capacity of network bandwidth, if the attacker can send 10 megabytes per second or more of data, towards that server, then that might not leave any capacity for legitimate users. The other limit often at the network is number of packets that can be handled per second. Routers maybe can only handle a maximum of 10,000 packets per second or something like that. Servers might have some limit on the number of packets they can handle per second. And so if the attacker can send more packets than that limit, then it doesn't leave any capacity for legitimate users, or it doesn't leave much for legitimate users. So you can see how these tend to lead to a different kind of attack. If you want to overload bandwidth, you probably want to send really large packets. And if you want to overload the number of packets per second, you want to send really small packets to minimize the attacker's cost. And then distributed denial of service, which you brought up, is a version of this denial of service attack that makes it harder for victims to defend themselves. And the idea there is the attacker doesn't send all this traffic from their own machine. The attacker gets a whole bunch of machines and sends traffic from all of them. And one common way to do that is the attacker hacks into a bunch of machines and forms a botnet, takes control of a whole bunch of 100 or 1,000 machines. Might be random people's home PCs that they haven't upgraded, but pretty easy to hack into. And then the attacker starts using each one of those to send lots of data towards the target, towards the victim server. This is a challenging attack to defend against because it's not easy for the victim to block the malicious traffic. If it's just the attacker sending malicious traffic from their own machine, then the victim can figure out, I'm getting a whole bunch of malicious traffic from this one IP address. Let's block all traffic from that one IP address. But if it's coming from 1,000 machines, it might be hard to tell what to block, what's legitimate and what's malicious.
Yeah, I feel like vanilla, like non-distributed, like denial of service actually like still relevant, or like this, because I feel like every time I hear about some form of denial of service, all, and then it's like it's all distributed, like is there still a place for like the regular?
I think distributed is a lot more common, precisely because it's harder to block. Yeah. I guess the only advantage to non-distributed one is you don't need a botnet. Another interesting kind of network denial of service attack is amplification. Amplification is interesting. It's where we exploit some patsy to help amplify the strength of our attack. Okay? So let's suppose there's some victim server and we want to overload their network bandwidth. But my network connection is too small. I can't overload their network bandwidth. I don't have enough network capacity on my machine to overload them. What I do is I find some patsy who does have enough network bandwidth and trick the patsy into sending lots of data to the victim. So how do I do that? One example of a way to do that is if the patsy is a DNS server, I send a DNS request to the DNS server, look up some host name that I know will trigger a long response. When I look up that host name, the answer has a whole bunch of records in it and a whole bunch of information, alternate IP addresses, information about this zone, whatever. Maybe I can send a 100-byte request and what will come back will be a 1,000-byte response. And then the attack part is the attacker sends a spoofed request with a spoofed source IP address to make it look like it came to the victim so that the patsy, the DNS server, will send the response back to the victim. Does that make sense? You with me? So an attacker who has a network link that could send 1 megabyte worth of data might be able to cause a 10x amplification and cause the victim to receive 10 megabytes per second worth of data if the patsy can send 10 megabytes per second of data and can be fooled in this way. Any guesses why DNS? I picked the example of DNS. Yeah? Because it's UDP. And why is UDP relevant? UDP doesn't have the security that TCP does. Specifically, what makes this kind of attack harder to do with TCP? Yeah? You got to do that SYNAC handshake. And that makes it hard to do spoofed, set up a connection with a spoofed source address. So you won't be able to do this kind of attack with a spoofed IP source address with TCP. But with UDP, you can. And DNS uses UDP, is one of the most prominent services out there that uses UDP. Okay. So that's amplification. And notice here how this is another example of asymmetry, where the attackers found a way to send a small amount of data and then cause the victim to receive a lot of data because of that like amplification factor. 100-byte requests led to a 1,000-byte response. That was a 10x amplification. So it's like a 10x asymmetry. The attacker spends, $1 and the victim has to spend $10.
And when I have like stupid is you have like one source machine, create a bunch of like sort of virtual machines and some like a big machine that can actually test it. It seems like you can still complete like a TCP handshake with those like virtual machines. Since I don't know, is it significantly easier to make a machine that can send a request than one that can make a request?
So I don't need to create, it turns out I don't even need to create virtual machines. If I control my computer, I can ask my computer to send any packet I want with any fields in the headers that I want. Normally, it's going to put my IP address in the IP source address, but I can replace that with any other IP address I want. It doesn't have to be my own. It could be someone else's. So it's really easy to send a spoofed packet, a packet with a lying, deceptive, fraudulent IP source address. That's easy. The hard part is the response will be routed to whatever IP address I put in there. And if that's not my IP address, it won't be routed to me. It'll be routed to some other machine. I won't see the response. So that's what prevents me from setting up a TCP connection. I'm sending something, but I can't see the response. And if I can't see the response, I can't finish the three-way handshake. So it would be easy for me to send 100 packets with 100 different IP source addresses. But I couldn't create 100 TCP connections like that because I wouldn't be able to finish the three-way handshake. So what distributed denial of service attacks do is the attacker compromises 100 real machines with 100 different IP addresses. Finds 100 people who have, I don't know, home Windows PCs. It's still running Windows 9 or something. It was easy to hack and compromises that with some virus or something like that and takes control of their machine. And now the attacker controls machines that can send packets without any spoofed addresses. So they can send packets, see the response, finish the three-way handshake, send denial of service. All right, so to defend against network level denial service, typically what we need to do is we need to block the bad packets at the network level or have excess capacity. If all the denial of service traffic is coming from one IP address, then it's not too hard to configure one of the routers along the way to drop all packets from that source address if it's known to be malicious. But in a distributed denial of service attack or with spoofed source IP addresses, there's no IP address to filter on. It's not easy to filter bad traffic. So the other defense is over provisioning. Make sure we have plenty of excess capacity. And that can potentially be expensive. I wanted to show you one more denial of service attack that's just kind of cute. It's not important, but it's got a cute theme, so I want to show it to you. And that's SYN flooding. Not an attack that is prevalent today. At one time, 20 years ago, it was, but not today. And SYN flooding is, again, a resource exhaustion attack. And what it exhausts is a limit on how many TCP connections a server can keep track of. When you open a TCP connection with a server, it has to have some region, some bit of memory for keeping track of information about that connection. Each connection that's open takes up a little more memory. So the TCP software will have some limit on the number of open connections it can handle at one time to limit the amount of memory usage. So what the attacker does is tries to open lots and lots of connections to use up all of those available slots. And when all those available slots are used up, then the server can't accept any more connections and legitimate users can't connect because legitimate users can't create a TCP connection to the server. That could be expensive for an attacker to do because the attacker has to set up that many connections. So SYN flooding is this trick to make it less expensive for the attacker, and even though it is more expensive for the server. And in particular, the expense for the server is like storing some state. The state that needs to be remembered after a server receives the SYN packet in this three-way handshake is it needs to keep track of some information like the sequence number, the initial sequence number X that was chosen by the client. And maybe there's some other information about this connection it needs to keep track of. So as soon as the server receives a SYN packet, the first packet in this three-way handshake, it like allocates this region of memory for storing state information about that not yet open but partially open connection. In the attack, what the attacker does is send a whole lot of SYN packets, but never follows up with the rest of the handshake. So the attacker sends like 10,000 SYN packets. For each one, the server responds, allocates a little more state for that partially open connection until the server has used up all available slots. And now it will not, it just ignores any more SYN packets because it doesn't have any more space to keep track of any more pending connections. The attacker doesn't have to store anything because they're just sending SYN packets with random sequence numbers. Okay, so for a while, this was a very simple way to cause a server to like stop responding to any new connections. Now, if the attacker sends all of these SYN packets from their own machine, it's really easy to detect and figure out because the attacker's source address, like the source IP address is the attacker's IP address. So you, like, system administrator notices my server's unreachable, what's going on? Oh, all these pending SYN packets from the same IP address, what the heck? Easy fix, block that IP address, boom, problem solved. So what does the attacker do to try to make this harder to block? What are you thinking? Fake the source IP address. Use a spoofed source IP address. And then you can't filter based on it. Yeah. So filtering is hard. It's hard to filter because it's almost impossible to distinguish legitimate SYN packets from malicious SYN packets. There's really nothing to go on. You can't go on the source IP address. There's not much information in the SYN packet. Any attempt to create a new connection looks alike, whether it's malicious or benign. So filtering to try to block the bad traffic, hard. Over provisioning by like trying to give the server more memory so it has more slots, kind of limited. So there's another defense that was implemented when this attack became a real problem that I thought is clever. It's called SYN cookies. And I want to show you the defense so that you see the idea behind it. Not because SYN attacks or SYN cookies are super important, but because it has a cute idea. Okay. So the idea is rather than having the server have to remember some information, store some state when it receives the SYN cookie, which imposes a cost on the server. In SYN cookies, we don't do that. When the server receives a SYN packet and has some state it would like remembered, it doesn't store that state in memory. It sends it to the client and tells the client, I'm going to need to know this in the future. Please send it back to me when you send me the third packet in the three-way handshake. It's kind of a funky idea. Like make the client store this data. The server doesn't store it. The server makes the client store it. So it puts the cost onto the client. Okay, so it conceptually is something like this. The client sends a SYN packet. Normally, the server would now allocate some memory to store information about this pending connection. But with SYN cookies, no memory is allocated. Instead, the server takes all that information that it would have stored in memory, that state, adds it to the response packet that the server sends, the SYN-ACK packet, as another field. And the idea is that we modify the protocol so that when the client receives this SYN-ACK message with this extra field, it will respond with an ACK packet as normal, but include that state, copy the state over into its ACK packet. At this point, the server now has the state again. Didn't need to remember it because it's present in the packet. The server can now allocate memory and store that state in memory after receiving the ACK packet from the client. So why is it safe or okay for the server to allocate memory after receiving the ACK packet, but it wasn't okay or safe for the server to allocate memory after receiving the SYN packet? What's the benefit? Either way, the server has to allocate memory eventually. What are you thinking? To do this attack, the client has to send 2 packets.
The worst case is actually flipped, because now the client has to store all this in ACK data while this connection is establishing, and so they're very hard to how many.
Client has to store data while this is in progress. So during that period, it's the client that bears the cost, not the server. Proves the client controls that IP. To finish the three-way handshake, finishing the three-way handshake shows that this is not a spoofed IP address. It's easy for an attacker to send a SYN with a spoofed IP address, but it's hard to complete the three-way handshake. So if we've completed the three-way handshake, then it's reasonable to allocate some memory for this connection, because we know what the client's IP address is. We have an IP address that we could use for blocking or for tracking down the source of the attack. But we don't want to do that after receiving the SYN packet, because after receiving the SYN packet, we have no way of knowing whether the source IP address is real or not. It could be spoofed, and it would be it's not reliable. So we only store state once we have a reliable way to identify the client, the user, an source IP address that we know wasn't spoofed. Yes?
I guess internally it's just possible because over TCP, I suppose. No, this is before you establish a connection. How do you do this? Do you just hash the state that you want, or do you raise a flag that says send this info back to me or something?
Yeah, good. How do you do this? The simplest conceptual way is you take all that state you would put in memory. It's just a bunch of bytes. That is included verbatim in the packet.
Okay.
And then it's copied over into the client, copies that into the ACK. And then when the server receives the ACK packet, it copies that into memory.
Is that a different protocol than standard TCP?
That's a different protocol than standard TCP.
So the client might not.
So you're right. The client would have to support this special extension or modification to TCP, which is a major problem. You put your finger right on it. And in my next slide, I'm going to talk to you about what we do about that major problem. So that's a major problem with this. It's also an issue that I'm sending more data. Yeah, back and forth. We're there's more network load. The more amount of state or information that has to be saved on the server, the longer the This, the more this blows up these packet sizes. We're fortunate because the amount of information that needs to be saved after the server receives a SYN packet is not very much. But if it was a lot, then this would be bad from a performance perspective.
What's stopping me?
Nothing. Nothing's stopping the user from spoofing the same IP, using their own IP. Nothing stops the attacker from using their own IP many times, but it's just very detectable and easily blocked if they use their own IP. If an attacker uses their own IP and they send these, thousands of packets per second, pretty soon some administrator is going to notice and they're going to block them in the firewall, and the attack's going to no longer be effective. And by the way, maybe the system administrator will report them to their ISP, and their internet connection will get blocked by their ISP. And so it's kind of enough of a disincentive that is not very attractive for attackers to do this attack if it's easy to block them or easy to identify them.
I think I'm missing why you can spoof the first SYN.
Yeah.
And have no repercussion for not be able to spoof the second.
Yes, good. The attacker can spoof the SYN with no repercussions, and they could spoof the ACK packet with no repercussions. But the tricky bit is, if the attacker has spoofed the source IP address in the SYN, then the response, the SYN ACK, doesn't go back to the attacker. It goes to some random third party. So the attacker doesn't see the value Y. So when the attacker tries to send this ACK packet, they don't know what to put in here, the value Y. And the server, will reject their packet or something. Yeah.
If the server is just gonna expect to find their state that's sent back,
Yeah.
why can you not just spoof the state?
Right, and that's another big problem with this. Thank you so much. You're totally. I love it. I love it. I love it. So there's another problem with this scheme, which is a client is supposed to send back the same state they got, but there's nothing that prevents the client from sending some other state. So this could open up a different problem of a malicious client that's not spoofing anything or not doing any denial of service, is just lying about what the state should be. Why is that safe? Oh my gosh, that doesn't feel good. Make state something that's computationally infeasible to guess. It's not so much the secrecy I'm worried. Yeah, I guess the secrecy is an issue. Yeah, okay, if there were any secrets stored in that state, that's revealed to the client. And it's also integrity, that the client could lie about what the state is, send back something other than what it was asked to respond with. What is inside state? Yeah, good question. Maybe we should look at that. Before we look at that, can you think of any tools we've learned in this class that the server could use to protect against those threats? To make sure the client doesn't make up some bogus state or doesn't learn what the value of the state is? Encrypt it, or put an HMAC, put a message authentication code. The encryption would prevent the confidentiality of any secrets in the state. MAC would ensure integrity to make sure the client can't lie about what the state is. Cool. So we could actually have the state be some encrypted MAC'd value, and that would solve that problem in principle. Yeah. Good? Okay. So we come back to the, still have this issue of this needs a new protocol or a modification to the TCP protocol. The client has to support it. What if the client doesn't support it? So this was the core idea, but initially people said, well, that's worthless because people's clients don't support this. And then someone came up with this clever hack, this clever hack to make it work with the existing TCP. And the clever hack they have is to send the state when the server has to pick an initial sequence number. The initial sequence number it's going to pick is going to be this conceptually encrypted HMAC state. instead of randomly picking an initial sequence number, it's going to pick the initial sequence number as this like encrypted HMAC state. And then the response that comes back, clients are supposed to return a copy of that initial sequence number. And so now clients will automatically respond by copying back that state. We don't need to modify the client in any way. So then to fully understand this, you got to work out what's actually stored in that state. And I don't know, we'd have to look up the spec. I'm not sure. We're very fortunate that there's only a handful of bits of state. So the server can have a handful of bits of state and some handful of random bits and encrypt that in some very concise way and then append a very short MAC that's not very secure, but it's like 8 or 12 bits or something like that. Just enough that it's the attacker most of the time will not be able to succeed at filling in with a bogus value. Okay, so there's a lot of the engineering details of how do you actually implement this, given that the initial sequence number is only 32 bits, is like some hacky bit fiddling something that I don't understand. We'd have to look at the spec. But the conceptual part I thought here was really clever. If the server has to do some work before we figured out who the user is, just don't and make the server pay the cost instead. Is like a little trick you could look for if you're feeling really stuck for how to deal with denial of service. Is there some way that I can shift the burden from the server to the client? Okay, that was what I wanted you to get from Syn cookies. I hope it made sense. Questions or comments? No? Okay. So firewalls, moving on. I'm shifting topics now from denial of service. In denial of service, we talked about if I've identified that some one person or machine is attacking me, I can try to block all the network requests they're sending to me. Firewalls are kind of a more general tool for not just blocking stuff that I know is bad, but limiting network traffic to try to prevent network-based attacks, not just denial of service attacks, but all attacks. And the idea here behind firewalls is think of yourself as like a system administrator for some large organization, for Berkeley. And you need to protect, you're worried about the security of like thousands or tens of thousands of laptops and desktops that the employees and the students and everybody have. And it's really hard to like, I don't know, check if all of them are fully updated or make sure they all have security software or protect all of them, know what you need to do, and even understand what machines are on your internal network. You'd really like some way to protect the company or the university as much as possible as you can. Probably the primary risk to worry about is external attackers, people outside UC Berkeley, somewhere in the world who are trying to hack into one of our machines. And so it's kind of like the network connection, that internet connection that is the conduit through which attacks might come in. They might be attacks from the outside world coming in to attack Berkeley machines. So if we want to try to protect the Berkeley machines, we could try to protect them by somehow controlling or limiting the network traffic that comes from the outside world into the UC Berkeley networks. And the idea is to have some like single point of access that can like monitor the network traffic and like figure out which network traffic should be allowed and should be disallowed, to have some control to try to limit the risk of attacks from outside entities. Okay, so the idea is you have the outside internet. This is the big bad internet that might contain all sorts of attackers. Then there's the inside UC Berkeley networks that contain all sorts of trustworthy UC Berkeley employees. And we're going to try to have a firewall, this monitor, mediator, limiter, access control, somewhere in between this connection between the outside internet and the inside network. Like maybe the border router, the router that is all internet traffic going out of UC Berkeley or coming into UC Berkeley goes through, that might be where we would put the firewall. So you can think of like a checkpoint at a airport where everybody who's going to any flight has to go through this one security checkpoint. It's one location where some security policy can be enforced. All the network traffic has to flow through this one point. Your policy on what network connections are allowed can be enforced at that one point. So we have some policy that specifies what kind of network connections are allowed and what are not. Like maybe Berkeley employees are trusted, so Berkeley employees are allowed to access any internet website or make a connection to any outside machine they want, no limits. But people on the outside we're worried they might be malicious, so we limit what kind of connections they can make to machines inside. They can connect to web services inside maybe, but not to like printer ports, so they don't start attacking our printers. Or, you know, we pick some like high-risk network, some high-risk machines like the payroll machines. No one on the outside internet should be able to connect to a payroll machine. So block all incoming connections from the outside world to one of those machines in the payroll department. That's the idea of a firewall. And if you have a home internet, your home internet router has a firewall on it, usually by default. And the default policy, typically, to try to protect your machine, which we know might not be fully updated, might not be running all the latest, greatest security software, typically comes pre-configured with a default policy that says your machine can make outside connections from your machine to the outside world, whatever ones it wants. But there's no inbound connections allowed. Outside machines are not allowed to make a connection to your home PC. Your home PC can't serve as a server. That's kind of a standard default policy on most people's home routers that are provided by their ISP. Or maybe inbound connections to some specific ports or specific services could be allowed, but all others would be blocked. That'd be another example, default policy. So a firewall is a device to try to enforce that policy. We need to have some defaults in your firewall. What should we do about connections if the policy doesn't say anything about whether they should be allowed or not? You could have a default of default allow everything except for those connections that explicitly should be blocked. It's a default allow policy. Or you could have a default deny, block all traffic, only allow if it's on the list of explicitly allowed connections. And this is just a trade-off between security and usability. The default allow policies is less likely to like prevent you from getting useful work done, but is usually less secure. Because if I make a mistake and there's something that I forget to block, then now I've opened up a way that someone could attack me, and I probably won't notice it until I've been hacked. With a default deny policy, it trends more towards the security side. So it's secure. If there's some network service or connection that I forget to allow, then I'll be safe. But maybe I can't go to that website I want, or I can't run the game that I want. The good news is I will usually notice that the game is not working. And so if I'm like a system administrator and I'm aware, then I can say, oh, I need to go allow, you know, connections to Steam, or I need to allow Valve to connect to my home PC or whatever. Need to add something to the allow list. So the security principle in the very first lecture, consider fail-safe defaults. The fail-safe default here would be a default deny policy. This is kind of abstract, and I think maybe I should start trying to do some more concrete examples. But I think we've been gone long enough that we need another break. You with me? You buy that? Okay, let's take a break. Let's take a 5-minute break. Okay, let's talk about firewalls. This part might be a little bit on the more boring side, so I apologize. I wish I knew a way to make this more interesting. But I wanted to tell you a little bit about some examples of how people have built firewalls. An example of a policy that you might want to use a firewall to enforce is allow anyone to make SSH connections to my desktop machine, but don't let them make, I don't know, connections to like FTP or to other port numbers that have been associated with network services that have often had vulnerabilities. And in EECS, the policy is by default, no one can make a SSH connection to my desktop machine in my office unless I go ask a system administrator, say, could you put my machine on the allow list? I want people to be able to SSH into my machine. And then they'll put it on the allow list. So they have a default deny policy. Okay, so the firewall has to then enforce that policy. And the typical way of building a firewall is a packet filter. It's like something on a router that looks at every packet that goes through that router and checks that packet against the policy to see if it should be allowed or denied. And if it should be allowed, it allows the router to forward it on like normal. But if it should be denied, then it blocks the packet, it drops the packet, it does not forward it onto the next hop. And the earliest firewalls were stateless packet filters, meaning they didn't keep any history or any memory. They looked at just each packet and the policy, but they didn't remember anything about other connections or past packets. And they just tried to decide in isolation, looking at this one packet on its own, should it be allowed or denied? And it turns out that's kind of tricky. Let's take the simplest possible policy we could have. The simplest policy we could have is, like for my home PC, allow all outbound connections initiated by my PC, but block all inbound connections initiated by someone outside on the internet. And if we think about how my access point, my router, my home Wi-Fi router could enforce that policy, when it sees a packet, it has to tell whether that packet is associated with a TCP connection that was originally initiated from the outside or originally initiated from inside. How do you do that when just looking at one packet without remembering past history? Turns out there is a hack that lets you sort of approximate that for TCP, which is kind of crazy. Like a packet that is coming inbound from the outside world into my PC, it could be a connection request initiated by someone on the outside, or it could be that I initiated the connection, that's a response to something I sent. If it's initiated from the outside, we want the firewall to block it. If I initiate it and it's a response, we want it to be allowed. In either case, it's a packet coming inbound. And the hack is you look to see if it has an ACK bit. So if the outside world initiates a connection, they'll send a SYN packet that has no ACK bit. So if there's no ACK bit set and it's coming inbound, the firewall should block it because that might be a start of a new connection. That will prevent creation of TCP connections that are inbound. If it has the ACK bit set, then it might be associated, it might be a response to something on an outbound connection that was previously initiated. And so if it has an ACK bit set, it can be allowed. It's kind of crazy, but it mostly works. And the kind of the surprise here is, that you can do anything at all, that you can enforce this policy at all without any state. It seems like there shouldn't be enough information to enforce the policy, but there sort of is in the kind of the kludgy way. You can't do this for UDP though, turns out. So for UDP, there's just no way to distinguish between an inbound packet that was initiated on a connection initiated from the outside or a response that's an inbound packet that was a response to something initiated by someone on the inside. So UDP, you just have to block all UDP connections if you have a stateless packet filter. Not very helpful.
still just send like. How much?
If the firewall blocks all inbound connections, it might prevent some of these denial of service attacks.
So
Like the SYN attack, the SYN flooding attack would be blocked by a firewall that blocks all incoming connection requests, because that firewall would block incoming SYN packets.
so like if like without and like does it take a lot of resources to block?
Right. Okay. But it doesn't solve attacks that overload my network link, because the slow link is probably a link from my home to my ISP. And if someone sends, if that's a 10 megabit link and someone sends 10 megabits of traffic, by the time it gets to my router, that network link is full. Even if I block it at my router, that still the network link to my home is full. Yeah, so to stop that kind of bandwidth-based denial of service attack, bandwidth exhaustion denial of service, really we need our ISP to block those packets. So the firewall in my home is not enough. Yeah. This, what I'm describing here is stateless, because it doesn't keep, the packet filter doesn't keep track of past packets or connections that are currently open or anything like that. There's no state. Just look at each packet and decide independently for each packet, regardless of what has happened in the past. Yeah. So this is not probably the best way to build a packet filter. A better way is a stateful one that can keep track of past information. Yeah.
How is it checking whether or not that whatever ACK packet it got has an action point?
Yeah, how does the firewall check where the packet's coming from? If it's on my home network, so it's my home router, then my home router is a router. So it's connected to my Wi-Fi network, and it's connected to the cable that goes between my home and my ISP. And it's responsible for forwarding packets like between the two. So if the attacker gets on my home Wi-Fi network, then the attacker is inside and they're not limited by this policy. So the firewall tells where the packet is coming from by, did it receive it from the wire from the ISP, or did it receive it from the Wi-Fi? Yeah, that's right. That's right. So if Berkeley puts a firewall at the router that is our border router, the router that connects us to the rest of the internet, what that can do is it potentially can defend us from some attacker somewhere in Moldavia trying to attack our internal machine. But it cannot stop one internal machine from attacking another internal machine. Yeah. So sometimes these firewalls are called perimeter defense, because once the attacker is inside, they don't do any good. I've heard it called like crunchy exterior with a nice soft creamy interior. Yeah. Okay, so stateful packet filter, probably a better way to build a firewall. And a stateful packet filter typically will keep track of some information, typically keep track of all of the connections that are currently active, and whether they were initiated by someone on the inside or initiated by someone on the outside. And there's some rules that control what connections are allowed or denied. And then each packet, when it sees a packet, it matches it up to one of those connections in the list of currently active connections it's maintaining, and uses that to figure out whether the packet should be allowed or blocked. And so our policy might have rules like shown here on the slide, like allow connections from host 4.5.5.4 to 3.1.1.2 if the destination port is port 80. That'd be an example rule. So these you can match on the source and destination IP address and source and destination port and which network link the connection was initiated from, internal or external, and have some, put some wildcards and have some rules in there about which connections are allowed. And if it's an allowed connection, then the packet filter, the router forwards the packet. And if it's a disallowed connection, then the router doesn't forward the packet and the packet just stops right there. Okay, so now this allows us to enforce more flexible policies about what connections are allowed based on like port numbers. Okay, so for instance, if we wanted to allow connections to an internal machine that is a web server running some marketing stuff, we could add a rule to our firewall that says allow incoming connections to this internal IP address, port 80 or port 443, but don't allow connections to other port numbers, so they can't connect to other network services on that machine. If the marketing department didn't configure that machine very carefully and is running other network services, they won't be exposed to the outside world. We don't have to worry about whether they are properly secured or not. If I have some printers internally, I don't have to worry about someone like trying to hack into my printers because there's no rule that allows connecting from the outside world to those printers inside. Stateful packet filters also open up another opportunity. They can keep track of the data that is being sent by the application and what is happening in that connection, and decode the meaning of that, and then have more fine-grained control over what's happening in that connection. Like if it's a connection to a web server, it can keep track of what URL is being requested and allow access to some URLs and block access to some URLs, for instance. Yeah. Is that what? Tell me again what the... yeah, I think it is. I think it is. I'm not sure whether it's a stateful packet filter or whether it's a application proxy. I haven't set up one myself. I'll tell you what an application proxy is in a moment. It might be a proxy rather than a stateful packet filter. Okay, so for instance, used to be that people would make files available by FTP servers. And the FTP server would have a username anonymous. So make stuff publicly available. The anonymous user had no password. So you could go download files from someone's FTP server by making a TCP connection to their FTP server, logging in as username anonymous, password blank, and then download files. But also, you could log in as one of the users on that server if you knew the right password. So, for instance, a policy that people wanted to enforce was, I want to allow people to connect to this FTP server as anonymous and download public stuff that we're sharing with the world, but I don't want them to try to log in as root, like to connect to the FTP server and try to log in as root and start guessing the root password. So then you could have a stateful packet filter that tries to enforce that policy, that monitors the data in this TCP connection, the payloads in those packets, and looks to see if it is an FTP connection, whether or not the payload, the data, contains the command to log in as root. And if it is, block that connection. Don't forward that packet. Don't forward any other packets associated with that connection. Okay. But this is a little tricky now to implement this kind of stateful packet filter because it has to keep track of a lot of data about the TCP connection to be able to make sense of the packets. So let's take a very simple policy, not something someone would actually deploy in practice, but just to get you thinking about some of the challenges. Let's imagine our policy is any connections, if they contain the string root, we want them to be denied. So if this has, ROOT, those bytes, then the connection should be denied. And we want to build a stateful packet filter to enforce that policy. Maybe because you're the Berkeley system administrator, the Berkeley security team, and you don't trust people inside who are running FTP servers to configure their FTP servers in a secure way. You want a second line of defense. So how would you implement such a packet filter? It's kind of tricky. The obvious thing would be to have your stateful packet filter look at each packet and look at the data, the payload part of that packet, and if it contains the sequence of bytes ROOT, then block that packet and allow all others. Okay, is that implementation strategy, is it clear what we could consider? Now I want you to tell me why that implementation strategy sucks. It's not a good solution. Tell me some ways that an attacker could defeat this stateful packet filter, could bypass it, could still manage to log in as root without getting blocked by this packet filter. Yeah? Escape the characters. So if R can be represented in some other way, like on the web, you can use percent and then the hex representation of the ASCII of that letter. And then it wouldn't look exactly like an R from the packet filter's perspective, and it wouldn't get blocked. Okay, good. Yes, escaping characters. I like it. Yeah? GCP lets you break up the data into multiple packets. Split it into 2 packets. The attacker could send this so that RO is in one packet and then OT is in the next packet. This implementation strategy won't block either one of those. Any others? Okay, that's a good set. So now we can think about what could a packet filter do to try to defend against these attacks. How would be a better way to defend? So let's start with your attack, splitting this up into multiple packets. What could a packet filter do to try to defend against an attacker who's trying to bypass it by splitting stuff up into multiple packets? Yeah? Have an FSM finite state machine that starts at R. Keep track of how long of a prefix of ROOT have you seen so far. When you see one packet, if it ends with RO, then keep track. I've seen the first 2 bytes of that. And then if the next packet starts with OT, then I know I need to block it. Yeah. And if you want something that's easier to implement, then another possibility is the stateful packet filter could keep track of all of the bytes that have been received in the past and kind of concatenate them all together and then do substring search on that concatenated buffer. That would take more memory. I like your FSM better because it takes less memory and is probably more efficient. Yeah?
Rather than allowing those.
Yeah. Yeah, this is a crappy policy. I agree. I picked a policy here that's probably not something you'd really want to do in practice because this is a default allow, which we've already said default allow is so many security pitfalls.
And the GCP word, there's really only TCP happening, therefore, there's false negatives.
Yeah. You're right. If you had a sufficiently limited allow list, maybe these challenges wouldn't come up. Yeah. But if you have more complex policies, they can arise sometimes. Okay, so you mentioned a problem of splitting the word root across multiple packets. Another problem is they could be split across multiple packets and be out of order. So that's going to make it hard to use a finite state machine because they might appear in a different order. And the end destination will put them back into the proper order. So the stateful packet filter has to keep track of packets it's received in the past and put them back into the right order. Kind of duplicate the same processing that the end destination will do. Another way that an attacker could bypass this, like obscure, crazy attacks, attackers can there's other various fields in a packet. Another field in their packet is the time to live, which gets decremented by 1 through each hop that it goes through, and then when it reaches 0, the packet's dropped. So it limits how many hops the packet can go through. An attacker, normally that's set to a large value that's large enough that's be plenty to get to the destination. But attacker could do a crazy thing where they send a whole bunch of packets. Each packet has 1 byte in them with a different TTL for each, setting the TTL to be smaller for some, so that it'll reach the firewall but not the end destination, and larger for others, so that for others it will go through the firewall and also make it all the way to the destination. So the ROOT packets have a larger TTL and will be received by the destination. The other packets have a shorter TTL, so they go through the firewall, they're allowed by the firewall, but then they're too small to reach the destination. So when the firewall is trying to reassemble these packets, it's really hard to know what is actually going to make it through to the final destination. Yes. That is also true. This is a different TTL. There is a TTL in DNS records that is how long to cache, and then there's a TTL in IP packets that is maximum number of hops for this packet to make sure the packet doesn't go in a loop and live forever, get forwarded forever. Yep. Time to live? Yeah, I think it does. Yeah. Alas. So there are these crazy ways that the attacker can send data that creates ambiguity that makes it hard for the packet filter to predict what will be received by the endpoint. Super painful to build a packet filter that can deal with all of these complexities. You can easily end up with situations where there's, from the packet filter's possibility, exponentially many possibilities about what the destination might receive, because we have 2 packets both sent with sequence number 4. Which one's going to be accepted by the end destination? Is it the first one or the second one? And then 2 possibilities for sequence number 5. Is it the first packet or second packet? So stateful packet filters have some limitations. Typically, either they can be bypassed or they have to maintain state in a way that can make them vulnerable to denial of service attacks. So another architecture for building a firewall is called a proxy. There's a proxy firewall and an application proxy firewall. And in the proxy-based schemes, the firewall is not some passive monitor that is just watching the packets and then blocking or allowing them. It's actually an endpoint of the TCP connection. So in a proxy firewall, there's 2 TCP connections. There's a TCP connection from the outside machine that's trying to connect, that's terminated at the firewall, and then the firewall initiates another TCP connection with different port numbers and sequence numbers and so on between the firewall and the inside machine that's being connected to. And the details of how that happened differ. In one scenario, the firewall kind of acts as a man in the middle. Oh, okay. And in the other scenario, some applications have a way to configure your browser so that it doesn't connect to the real server, it'll connect to the proxy instead. So there doesn't need to be any network level man in the middling. Um, you can configure that into the system. And there's some reason that this is a really powerful way to avoid all those problems I just showed you that I really struggle to explain. So I'm going to try. And if it doesn't make sense, maybe I'll try again and then I'll ask for your help to like see if any of you got it and can help explain it. It's really cool, but I'm really bad at explaining it. I'm so sorry. Um, the cool thing is that by having two TCP connections, like with the endpoints at the firewall, all of these crazy ambiguity attacks no longer can be used to deceive the firewall and make the firewall think that one piece of data is being sent and the final destination thinks something different. And somehow it's because the firewall like decodes all the TCP, figures out what's the stream of bytes that's being received, then like checks whether that stream of bytes should be allowed in some application, and then if it is, creates a new TCP connection and sends those new bytes over. And so now it's creating a new connection that's created by the firewall. So this new connection is created by the firewall. It's created in a way that has no ambiguity and contains the bytes that were approved. So it's like cleansing to remove all the ambiguity by taking something possibly expressed in some crazy ambiguous way and like normalizing it to a form that is easy to predict how the final destination is going to interpret it, and therefore we can check whether that should be allowed or not. You can see why I said that I'm really bad at explaining this. Does anyone understand and want to help your fellow folks out understand? I could use your help.
It's like unless the firewall is also executing whatever like the client is executing in terms of like reassembling the string that we get into like root or like some other method. I don't know why like having access to the actual byte stream would help avoid that.
Yeah, okay, I'm explaining it really badly. So if we think about this TTL stuff, if the client is malicious and is sending packets with varying TTLs, each one of those is either going to reach the firewall or not. If it doesn't reach the firewall, then like, okay, it might as well not exist. So let's assume it does reach the firewall. Then it doesn't matter what the TTL is, because the firewall is going to reassemble that into bytes. And then the firewall's TCP stack is going to send some new TCP connection, and the new packets will have a large TTL for sure. Because it's being sent by the firewall's TCP stack, which is, good and not malicious and not creating any of this crazy ambiguity. So it's like what's coming in is in some crazy format and it's being converted into an example. Okay, I'll try an example, but it's maybe really bad. An example is someone hands you this mess of code and you have to understand what it's doing, and it's like in some crazy formatting. So the first thing I do is I run a syntax normalizer, like white spacer, to like put it into standard white spacing, so that it's easier for me to read the code. Um, Bad example. Sorry. Yes, help me.
And all like TCP on the top of the package that the time of it is greater. But how do you make sure that the firewall is not affected by malicious attackers?
Yeah. The firewall, we have to make sure the firewall can't be hacked.
Yeah.
The firewall has a TCP stack that decodes these TCP packets and turns them into a bunch of bytes. And then it sends those with a whole new TCP packet. So it doesn't take the TCP packet received and add some more stuff. It sends a whole new TCP packet created from scratch. Yeah. Yeah. Okay, everything's in TLS doesn't give your hose with TLS. I'm going to come back to that one. TLS messes up everything, this whole story we have here. Does anyone? Yes.
two TCP connection.
They don't use the two TCP connections. The firewall doesn't like forward anything else. Won't forward anything other than packets destined to it. So that makes sure that everything has to go through these two TCP connections. Do you want to help me figure out how to explain this better? Either ask a question about how I can help you or explain it to your peers.
If the destination takes more hops in the firewall, the packet connects with the TTL.
Yeah?
I'm stuck there, set up.
Stuck there with a TTL attack. Good. Okay. Let's look at this TTL attack. Let's say that the client sends two TCP packets with the same sequence number. Let's just focus on this part right here. This part I'm circling. Two TCP packets with the same sequence number. What's going to happen if both of those are received by the final destination? One of those has an N in it and one has an R. Let's suppose both of them reach to the final destination. What will the final destination do? What's that? Whichever one reaches first, I think is correct. I think that it will take the N first, and then the next one will say, oh, I've already seen something with that sequence number, and ignore it. So I think that's right. Okay? So if the packet filter knew that both of these packets are going to make it through to the destination, the packet filter would know, pay attention to this N, ignore the R. Good? But with the TTL trick, the client, the attacker, the sender here, is messing with the packet filter by setting a low TTL on the N packet and a high one on the R packet, which causes that the N packet doesn't actually make it all the way to the end destination. It makes it partway there, and then this is 16 hops in, and the time to live expires, and it's like, oh, I can't go any further, and it stops getting forwarded by some intermediate router in between the firewall and the end server. You with me? So let's say from the source to the end server, it takes 20 hops. 10 hops to the firewall and another 10 to the final destination. Then 6 hops through here, the TTL will run out. It won't make it to the end destination. So if the packet filter is thinking, I should treat this as the end destination is going to be receiving an N, the packet filter is wrong. The end destination will actually be receiving an R. But if the end destination was close, was only 15 away, then the end destination will receive an N. So if the end destination is more than 16 away, the end destination is going to get an R. If it's less than 16 away, it's going to get a N. And there's really no way for the packet filter to know how far away the end destination is. So it's very hard. The packet filter is kind of screwed. It has no way to know whether the end destination is going to get an N or an R. In this example, it got an R, but it couldn't have known that.
Sequence number, it's already seen sequence number before. Why would it allow another sequence number for it to go?
Aha, that could be another possibility, is the packet filter could say, I've already seen one with sequence number 4, I'm not going to allow another. That is a reasonable defense in this case. Yeah, that is a reasonable defense. I think what you'd probably want to do is have the packet filter remember, when I saw sequence number 4, it was an N. So I'll allow sequence number 4 again if it's N again, because there could be retransmissions. But if it's the same sequence number but different bytes, I'm not going to allow it. So that would be a fine defense for this. It does require the packet filter to keep track of the old data. So it has to keep more state, so it could be subject to denial of service attacks. But the main point I'm reaching is not that this specific ambiguity is impossible to prevent. The main issue is there's all sorts of obscure features of the protocols that each single one could create some ambiguity. There could be 50 of these ambiguities, and it's really hard to implement a defense for all 50 of them. And the odds are that there's a 51st that you didn't think of. So stateless packet filters have some issues if they're trying to enforce some policy on the data. It's fine for like header fields. There's no doubt about how they're going to be interpreted. But for sophisticated policies on the payload, on the data, they're not reliable. Yeah.
In the path, and then like where would the one that's sending another TLS wrapper be?
It would be the that border router that Berkeley has. There's one router that all the Berkeley hosts, all the connections go through that goes to our ISP and then goes way out to the rest of the world. That at that one place. That's why we like firewalls, because there's one place where I put that stateless packet filter and it protects everybody. The same thing with a proxy firewall, be that one place.
And the only one is stateless, so if it doesn't pass, then I'm not going to look at it. And the other one is be like, I'm going to take all of them and then apply this packaging.
Yeah, the application proxy firewall has to be involved in every connection. So it is like a performance bottleneck. Yeah. Yeah. Yep.
The operator does not know whether they're increasing it or decreasing it because of confidentiality.
Because the IP protocol doesn't encrypt it, so we got to work with whatever is there. We can't change all the protocols. The idea of firewalls is they're not a strong solution, but they're an easy deploy solution that can protect a lot of hosts all at once. So there's some like leverage for the system administrators. And so part of that is you got to be able to make it easy to deploy with existing systems. If it's hard to deploy and requires changes a lot of existing systems, there's some other changes that I would rather make first to be more effective than a firewall. Yes. Yes, absolutely. Yep. 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 Totally. So I just spent all this time telling you about firewalls, and the answer today is they're almost useless today, at least for policies based on data, because most connections are encrypted. If they're encrypted, the firewall can't see the data, so it can't make any decisions based on the data. So, oops. Interesting how one security measure kind of is in conflict with another. And then some companies will use a mechanism where they they arrange so the firewall can decrypt the data, just so that they can have a firewall. Like they have a special certificate authority that does a man-in-the-middle attack on every TLS connection so that the firewall can decrypt all the data. Okay. Another concept that I wanted to tell you about is that of a VPN, a virtual private network. And a VPN is a way to have a connection, a secure connection from an outside machine to get onto the inside network. So let's suppose we got a firewall and it doesn't allow people on the outside to connect to any internal machines, but you're traveling. You flew to Canada for a conference, you're presenting a paper, and you want to log into some internal machines. Well, at Berkeley, we let you because we allow all inbound connections. But at most companies, you would not be able to connect to internal machines. So what do? How do you get some work done? The answer is a VPN. On your laptop sets up a secure TLS connection to some server inside the network, inside the Berkeley network, that acts as a router. And so when you're in Canada with your laptop and you want to send a packet to a Berkeley inside machine, that packet doesn't go over the public internet. It gets encrypted by software on your laptop, sent over that TLS connection to this internal host at Berkeley. And then the internal host at Berkeley decrypts it from the TLS connection and copies that packet onto the internal network. And so it bypasses the firewall. All right, so firewalls, positive central management of security policies gives system administrators like a lot of leverage. But the negative is they can block some useful applications. They don't defend against insider attacks. Once the bad guy gets inside the network, it doesn't prevent spread within the network. If a trusted employee takes their laptop and goes traveling abroad and then gets hacked while they're traveling and brings their laptop back into the internal machine, and with malware running on their internal machine, now that malware is on the internal network and it's not limited by the firewall in any way. Okay. So main ideas I wanted to tell you about were denial of service, ways you can defend against them in applications and at the network level, and firewalls. All right. So let's move on to next topic. Next topic I wanted to tell you about was intrusion detection systems. Oh, there was a question long ago. Can I explain how merge sort is safer than quick sort against denial of service? Sorry, Tenzin. I've just missed that for so long. Merge sort is safer than quick sort because quick sort has a worst case running time of O of n squared, quadratic. Merge sort has a worst case running time of O of n log n, which means there is an input to quick sort that makes it take O of n squared time. So an attacker could upload some data that is that worst case input that makes quick sort take a really long time. And if the attacker did that, then the server runs a really long time. And if the attacker does that repeatedly, it might overload the server and then other legitimate users can't use the server. So if we use merge sort, then that can't happen. There is no worst case that makes the sort take a really long time. Okay, so intrusion detection. I want to show you about intrusion detection because it's another method that is widely used that system administrators can get a lot of leverage, that by like one system administrator can try to protect an entire organization, thousands of machines. And it's got some pluses and some minuses that are worth knowing about. And the idea of intrusion detection is firewalls are trying to prevent attacks by blocking connections to potentially vulnerable services. Intrusion detection says we're not going to prevent anything. Let's just detect. Let's see if we can detect attacks or if we get compromised, a way to detect that we've been compromised so that system administrators can then clean up the hacked machine, upgrade the systems, kick out the attackers, respond in whatever way is reasonable. And there are a bunch of attacks, and I want to give you one example attack that we could like try to detect through intrusion detection, path traversal attacks. So we've looked at a whole bunch of attacks on web applications, SQL injection, cross-site scripting, CSRF. Path traversal is just one more that's a common one that's maybe worth knowing about. So here's how path traversal works. A path is like a way to identify a file. So usually it has like a bunch of directories separated by slashes. Also, you might find in a path the special names dot and dot dot. A single dot means the current directory, and two dots, dot dot, means the parent directory. Okay. So you might have some file system like represented in this box here, and you can think of a file system as a tree where there's directories represent internal nodes, and then like each file is some leaf in this tree. And you could represent the file evanbot.jpg by giving the fully qualified path starting from the root of the tree, /home/public/evanbot.jpg. Okay. If you typically program processes have a current working directory, the directory that's currently associated. You don't have to give the fully qualified path. The other is you can give a relative path relative to the current working directory. So if the current working directory is public and the file name is ./codabot, then it starts from the current directory and then it does this walk the tree. So dot means current directory, slash means go down from there, codabot.jpg, go to that file. And dots can occur in the middle of a file path. So if you have home/public/private/passwords.txt, the resolution this would lead to is you start at the top, you go to home, then you go to public, and then you go to ... which goes back up to home, and then you go to private, and then you go to passwords.txt. Okay, so ... means go up. Go to the parent directory, the containing directory. All right, so here's the idea of the path traversal. I want you to imagine we're building something like a file sharing site, like one you might have seen before. I wonder where. And the user enters a file name, and this file sharing site is going to allow them to download that file. But we only want people to be able to download files from the public directory. So the way this server is implemented is it starts with the string /home/public/, and then it appends to that the file name that the user enters. And it reads that file and sends it to the user. Okay, so if the user enters evanbot.jpg, then this program running on the server will construct the string /home/public/ and then append what the user entered, evanbot.jpg. So the file that will be read is the evanbot.jpg here in the public directory. And the intention of this application, let's say, is to allow the user to access any of these files in the public directory, but not things in the private directory. So here's the path traversal attack with all that set up. What happens if a user enters in the file name ... /private/passwords.txt? Then when the string concatenation happens, the server code will concatenate this fixed string /home/public with the user string ... end up with a file name that is home/public/... And we saw previously what that resolves to. That resolves to the passwords.txt file in the private directory.
That before whatever they put in as file name, it is put in, there's already /home/public.
How would they know? Typically guess and check, try some possibilities. Sometimes if the server's code is publicly available, like it's open source software, then the attacker could download that code and set up their own copy on their own machine and like understand everything that's happening. But a lot of websites, it's not public, so that's just blindly guessing. Okay, so that's known as a path traversal vulnerability. The intention of the developer was probably only expose files in this public directory, and they thought by starting the path with home public, it would make sure that it was limited to that, but because of the ... possibility, it actually exposed all files on the file system. So don't use string concatenation to build up file names, or you may end up with a path traversal vulnerability. Or you could not allow ... Yeah, you could separate out by slashes and make sure that nothing in there has ... Yeah. Most operating systems provide a way to like access one component at a time. And you could separate out by slashes and make sure that none of those components have a ... and access one component at a time and kind of do this traversal yourself one at a time, and that would be safer. Okay. So that's the vulnerability. It'd be really easy to end up making that mistake if you're not aware of it. Yeah. Okay, so I'm going to just use that as a running example of one kind of like attack that you might want to try to detect within an intrusion detection system. There are many kinds of attacks you might want to detect. And I, intrusion detection could be deployed at different places in your system. Maybe the most common way to deploy intrusion detection is a network-based intrusion detection system, sometimes called NIDS. What that means is you connect the intrusion detection system to the router. The intrusion detection system gets a copy of all of the packets, all of the network data, observes and monitors all of that network data and network connections, and sees if it detects any sign of an attack based on network activity. Another approach is a host-based intrusion detection system, which is we run some software on every machine inside the company that observes all the things that are happening on that machine and tries to detect any sign of attack. And a third approach is to monitor log files and try to detect any sign of attack. Any idea why we might choose a NIDS? Why we might prefer the network-based monitoring? Yeah? Can monitor all the hosts. I don't have to worry about, like, did this monitoring software get installed on every host? Maybe related, it's really easy to deploy. Connect this up to one router and boom, all the thousands of machines are being monitored. Yeah?
Cheap.
Cheap? Yep, cheap. Any ideas why we might choose a host-based intrusion detection system? Looking at you. Yeah? Different operating systems might have different vulnerabilities. How would be a host-based intrusion detection system be better for that? You could have a different monitor for each operating system that like checks for different things on Apple versus on Windows. Sure. Any other reasons why I might choose a host-based intrusion detection system? Yeah? Maybe different policies for different hosts. I want really careful monitoring on that payroll site that's managing a lot of money, but you know, maybe don't need to worry so much about the student researcher who doesn't have access to anything sensitive. What about firewalls? Why do we say a big problem with firewalls would make them a lot less effective today? Yeah? Yeah, a lot of network connections are now encrypted with TLS. So a network intrusion detection system is not going to be able to monitor very much. The data is encrypted. It can't tell what data is being sent. But a host-based intrusion detection system can monitor what data is being sent because it can observe the data before it's encrypted or get access to the keys. Yeah. Okay. So here would be a typical example of how a network-based intrusion detection system might be deployed. We have the big bad internet. We have this border router that connects between the internet and the inside machines and a whole lot of inside machines. And then the network intrusion detection system might be installed on the border router, observing all the data that goes through the border router. And the network intrusion detection system is kind of similar to a packet filter, a stateful packet filter in some ways. Like has a table of all the active connections. Every time it sees a packet, it like figures out which of the connections it's associated with. It keeps track of the data that's being sent on that connection. And if it sees a packet that's not associated with any of its known connections, and it says, oh, there must be another connection that I didn't know about, and adds that to the list of active connections. Similar to packet filter, kind of monitoring, except the action is different. It's not trying to block a packet, decide whether to block a packet or not. It's just doing monitoring and detection. And we talked about some reasons why we might like network intrusion detection systems. Protect a lot of systems with one go. But one drawback of network intrusion detection systems is this, again, problem of ambiguity. The same problem we had with stateful packet filters shows up here. That it can be unclear how how this data is going to be interpreted by the end host because of network reasons, or just because we don't know what version of software is running on the end host, and so we're not sure. Also, another big problem that we mentioned was encrypted traffic. All the connections that are encrypted, NIDs can't see the data, so can't do much monitoring. So the ambiguity issue, yeah, I don't know. We kind of talked about this, but just to see this in the context of like detecting path traversal attacks, a very simple thing that a network intrusion detection system might do is it might monitor all the connections to web servers, and if it sees stuff in them that looks like a file name with a ... in it, then it like sends an alert. I think there might be a path traversal attack happening. Emails a system administrator or something like that. But this is unreliable because what the NIDS sees might not match what arrives at the end host. Like because of TTL, because of packet reordering and data being split among multiple packets. Also because of issues that you raised before about encoding. The data could be encoded with a URL percent encoding, and a dot, I think, gets encoded as %2e, and a slash as %2f, something like that. I don't know. I don't remember. Anyway, you can encode the ... /etc/ password using URL encoding. And then that might be decoded by the end web server so that what appears in the packet doesn't match the ... etc password pattern that the NIDS was looking for, but that will still be interpreted the same way by the end web server. Now, if we know about this encoding, then the NIDS can like decode anything that looks like it might be encoded with this percent encoding. But we have to know all the ways it might be decoded. And we have to know when to do the percent encoding, decoding, and when not. Which data is going to be decoded and which is not. And if there's any differences among multiple web servers about exactly how they do the decoding, we have to know which of those forms of decoding is going to be applied. Also, the NIDS might lack some context. It might not know what the current directory of the web server is. So when it sees some crazy looking file path, it might be hard to know whether that actually leads to anything harmful or not. So should I send an alert? Maybe yes, because it could be an attack, but maybe no, because I don't want to cry wolf unnecessarily. So the challenges that face network intrusion detection system is imperfect observability. What the NID sees doesn't necessarily match what the end system sees. So this can lead to either missed attacks or to like faulty alerts. And also the other problem is that it can be hard to know how the data is going to be interpreted or parsed or decoded by the end system. For instance, if the end system is a web browser, different web browsers will interpret HTML differently. If it's syntactically valid HTML, it'll be interpreted the same way by all web browsers. But when many web browsers will try to take syntax errors in the HTML and correct them up somehow to try to do something reasonable. And Chrome will correct things up in a different way than Firefox. And probably it's hard for a NIDS to know which browser is present on the other end of the connection. And so when it sees some data, it might be ambiguous about how that's going to be decoded or interpreted by the web browser. Is this a Firefox or a Chrome? So is it going to be decoded like A or like B? And that might make the difference between whether this looks like an attack or looks innocuous. So there's some like fundamental ambiguity, both because information is missing, but also because when you have to write, the NIDS has to like write a decoder or a parser that exactly matches the parsing or decoding that's going to happen on the end system, and it's hard to get that an exact match. Okay, so this opens up the possibility for evasion attacks. And there are all sorts of sophisticated, clever, crazy, arcane ways to exploit inconsistency, find little corner cases where the NIDS will interpret things one way, the end system will interpret it a different way, and then the attacker deliberately sends attack packets that will be interpreted differently, be interpreted as malicious by the end system, but that the NIDS thinks is benign. So that makes NIDS possible to bypass if you put enough effort in. Often. It's hard to make them completely reliable. It can be very challenging to make sure that the end system and the NIDS are interpreting things in exactly the same way. One way to try to defend against this would be to have the NIDS rewrite the data. The NIDS interprets the data, decodes it, and then re-expresses it in some canonical, easy to interpret way that it's sure it knows how the end system will interpret. Like if it's got some HTML with some syntax errors, it tries to fix up the syntax errors, replace that with syntactically valid HTML that all the browsers will parse the same way, and send that to the browser. That would be possible. Usually we don't want a NIDS to do that because that involves changing the traffic. And what if it changes the traffic in some, it could break some website or cause some crazy, like that's scary. Start to say, we're going to attach something to your router that will change some of your traffic. And I pinky promise that, I won't mess anything up. So people usually are not willing to deploy a NIDS that does something like that. So that's not really a realistic option in practice. So these are kind of challenges that make NIDS, they can detect many attacks, but there may be ways to evade detection. Maybe ways to like make stealth attacks that a NIDS is not going to detect. And then the big drawback of most NIDS is that today many connections are encrypted using TLS, and so the NIDS can't monitor them. Ugh. Okay. Another option is a host-based intrusion detection system where we run some software, some agent or something that's running on the internal machines. Every internal machine is running this software that monitors all the things that happen. All the file system reads and writes, all the network connections and all the network data that's sent and received, all the processes that are created, any registry keys that are modified, configuration changes every time someone logs in or logs out. If it's running in sort of inside the operating system with root or administrator permissions, a host-based intrusion detection system can monitor everything happening on every machine. It's a pain to install on every user's machine. If you are a Berkeley employee, you may know that this past year, there's a new requirement that every employee has to install their monitoring software, some monitoring software on our individual machines. So up until now, it's been too much of a pain to actually do, but finally campus decided the problems are severe enough that we're going to require that all employees have to install this stuff on all their machines. Yeah, so maybe it could be all students someday in the future. Okay, so the benefit of the host-based intrusion detection system is better observability. It can observe a whole lot more that's not visible in the network, like files that are read and written, and can observe the data before it's encrypted. And doesn't have to worry about ambiguity or inconsistency because it can observe how the data was interpreted. Doesn't have to predict how it will be interpreted. But it's harder to deploy. Another approach that some places use is they monitor logs. And the only reason to do this basically is because it can be easier to deploy. Some places will tell everybody, configure your system so that they upload the logs to our central logging server, and then they monitor all the logs to look for signs of intrusions or attacks. So how do we have, yeah. Normally, most machines will store logs locally, but you can configure them to upload logs to a central log server. So if you want to evaluate an intrusion detection system, any kind of detector, there's two kinds of fundamental like numbers that matter that measure the two kinds of mistakes that the system can make. One mistake it can make is a false positive, a false alarm. That's where the detector sends off an alert. I think we're under attack, but actually there's no attack. The other kind of mistake is the detector is a false negative, where the detector doesn't realize we just got hacked, but the detector doesn't detect that. Okay, so typically when we evaluate a detector, we try to measure the false positive rate, the false alarm rate, and we try to measure the false negative rate. So those are rates. So out of all events, what fraction of, let's see, the false alarm rate is out of all the benign events, what fraction of them trigger an alert, a mistaken alert? And the false negative rate is out of all attacks, what fraction of them go undetected? So there'll be like a percentage. So to like think about a simplified version of this, can you build a detector with a false positive rate of 0%? How would you do that? Yeah? Never alert. Never alert. If you never alert, you'll never have a false alarm or a false alert. That's not very useful. It's also possible to build a detector with a false negative rate of 0. Always alert. Also not very useful. So neither number, it's not like we should just optimize for one in isolation. We have to like, it's a trade-off, right, between these two numbers. And usually you can't get both of them to be perfect. So you can make one better, but the other one gets worse. And so we're trying to find some kind of a balance between these two. And figuring out how to form that balance is tricky. But like if you think of like fire alarms, like smoke detectors, they're also the same deal. They're making a balance between those two. Like some of the times they go off and it was just I was cooking a steak and I burnt it and there was no actual fire. And okay, we figure that's kind of livable. We can tolerate that happening sometimes. What we really want to avoid is like the house is burning down around me and I'm asleep and I don't and I don't notice until it's too late. So like fire alarms, we really want a very, very low false negative, right? And we're willing to tolerate some false alarms. With intrusion detection systems and networks, it's a little trickier because of what's known as the base rate problem. And the base rate problem is that there's a lot, it's really easy to end up with too many alerts. I want to take an example of a detector that has a false positive rate of 0.1%. Only 0.1% of like benign things wrongly cause an alert. That sounds like a really low error rate, 1 in 1,000. But imagine we got a web server that's getting a whole bunch of requests each day. If it gets 1 request per day, 1,000 benign requests and 5 attacks per day, then we're only going to get 1 false alert. And 5, maybe let's say it's perfect at detecting attacks. So maybe we get 6 alerts and 5 of them are real attacks and 1 is a false alarm. That'd be okay. But if our web server becomes a lot more popular and now has 10 million benign requests per day and 5 attacks per day, then the number of false alerts I'm going to get is 10 million divided by 1,000. So I'm going to get 10,000 false alerts a day. So every day I get 10,005 alerts. 10,000 of those are completely harmless, and 5 of those are real attacks. So system administrators got 10,005 emails in their inbox today, and some 5 of those were useful, and the rest were complete waste of their time. That is a total boy cried wolf scenario. Such a system is completely useless. Very quickly, that system is going to get turned off. So you can see that to be useful, the false positive rate has to be incredibly low. Incredibly low. We're like looking for a needle in a haystack. And if the false positive rate is not exceptionally low, the system is useless. So we often are willing to tolerate a significant false negative rate just because we have to have a low false positive rate. Yeah. So usually intrusion detection systems can't detect all attacks. If they detect some of them, we feel like that something is better than nothing and we're happy. And you can see this problem come up in a lot of contexts in real life. You can, like, detecting terrorists in an airport is another example of this, where, like, there's like billions of people who fly every year. And how many terrorist attacks are there in the US? Like, let's say 0 approximately. And so, like, the false positive rate is going to be, I mean, unless your false positive rate is really low, you got a lot of false secondary screenings and so on. So it's a major challenge when most of your traffic is benign to build a intrusion detection system that is useful. There's more I'd love to tell you about intrusion detection, but I think maybe I'll save that for next time. So I think this is a good place to stop. Thank you so much. Have a great week. And I'll see you next Monday. We will have class next Monday, but no office hours or discussion sections next week.